Hi, I'm Nick Mosier. I'm a PhD student at Stanford, advised by Caroline Triple. I'll be presenting our work on Serberus, a comprehensive Spectre defense for constant-time cryptographic code. Security critical code like crypto code is carefully written to avoid leaking secrets when it executes. Here's an example crypto routine from Libsodium implementing the Salsa 20 stream cipher. I've highlighted the secrets here in yellow. So this is what we call a constant-time program. It avoids passing secrets to the unsafe operands of leaky instructions called transmitters. Common transmitters include branches, memory accesses, and variable time operations like division. However, constant-time programs only consider sequential executions of the program. That means they may still pass secrets to transmitters during transient execution, thereby leaking them. And so this is exactly what happens in a Spectre attack. So to see how this can happen, look at this call to load32, which returns the first 32 bits of the secret key. This is what load32 compiles down to an x86 assembly. It's just a load of the secret into the return register EAX and a return. Here's what the function call to load32 looks like in assembly. So sequentially, the secret doesn't leak because the caller simply stores it to the stack. However, the processor may mispredict the return address and return to a transient transmitter that leaks the secret. By transient, I mean the transmitter doesn't architecturally commit due to the prior misprediction. So this is called a Spectre attack. Spectre attacks exploit mispredictions to transiently leak secret data. Sources of these mispredictions are called speculation primitives, and there are 5 well-documented speculation primitives on modern processors. They are conditional branch prediction, indirect branch prediction, return address prediction, store-to-load forwarding prediction, and predictive store forwarding. So generally, these are named after the microarchitectural structures that implement these predictions. And so the misprediction on this slide is an instance of return address prediction, or RSB for short, named after the return stack buffer. So we present Serberus, which is the first defense to comprehensively secure constant-time code against Spectre attacks exploiting any combination of these 5 speculation primitives. So in designing Serberus, we had to overcome these 5 challenges. However, I'm only going to discuss these 3 and our solutions to them, and they are unconstrained speculative control flow, passing secrets, arguments by value, and how existing techniques for root-causing Spectre leakage are inapplicable to constant-time code. If you'd like to learn more about the others, please see our paper for details. The first challenge is unconstrained speculative control flow. And so first off, return instructions can transiently return to any instruction in the program, including ones hidden within compiled instructions. This is a possibility because x86 has a variable length instruction set. And so similarly, calls can transiently jump to any instruction, including hidden ones, and the result is this messy transient control flow graph that's impossible to analyze at compile time. So our solution is to use existing ISA extensions to constrain speculative control flow. Specifically, we use Intel Control Flow Enforcement Technology, or CET for short. This provides speculative CFI protections on some recent Intel microarchitectures, like Alder Lake N and Arizona Beach. In fact, in response to our work, Intel recently released online documentation of Intel CET speculative semantics, and this QR code here on the slide directly links to it if you're interested. So to start, we enable CET's indirect branch tracking. This ensures that calls and jumps can only transiently jump to end branch instructions, which we insert at each function entry point. Next, we enable CET's shadow stack and the RRSBA disable speculation control. Together, these ensure that returns can only return to call sites in the program. As you can see, the transient control flow graph is now much easier to reason about. So note that CET is not a Spectre defense in itself, it just happens to have some useful speculative semantics on some microarchitectures. So indeed, after enabling these constraints, the secret still transiently leaks, but at least now it only leaks along a single path rather than many. Before we move on to our second challenge, I'd first like to visualize Serberus's hardware speculation constraints. So transient control flow and data flow can be modeled as a two-dimensional plane where the origin represents only sequential control flow and data flow. But on the top right corner, we have the default operating mode of modern processors, which exhibit unconstrained transient control flow and data flow. And so we've already seen how Serberus constrains transient data flow. It does so with Intel CET and the RRSBA disable speculation control. Together, these ensure that transient control flow can't leave the control flow paths that are analyzable at compile time. However, unconstrained transient data flow is also a problem. It makes common static analyses like alias analysis useless, since a load may read from any store, including those to a different address. Serberus constrains data flow by enabling the PSFD speculation control, which ensures that loads can only read from prior same address stores. This allows Serberus to do a rudimentary speculative alias analysis, which turns out to be key to its performance. And so this is where Serberus' speculation constraints fits in relative to the larger range of speculation constraints. So the background here is a heat map of performance. It's logarithmically scaled, so darker red is much higher performance and closer to white is lower performance. We observe only about a 3% overhead with Serberus' speculation model. It's important to note this does not mean Serberus' overhead is 3%, just the speculation constraints required by Serberus are 3%, particularly on the Spec 2017 benchmarks. So 3% overhead. Now let's move on to the second challenge, which is that passing or returning secrets by value is inherently vulnerable to Spectre, since calls and returns are easily mispredicted to transmitters that'll leak the secret. So preventing this leakage is expensive. To do so, we'd have to insert speculation fences at every call and return target in the program. To overcome this problem, we propose static constant time programming. This extends constant time with two additional requirements. One, that all variables have static security types. Please see the paper for details on this. And two, that all secret arguments are passed by reference, not by value. So this latter constraint solves challenge number 2. So in our example, load 32 violates this second rule of static constant time by returning a secret value. We can easily make it conform, however, by having it store its return value in a pointer argument instead, like this. Unfortunately, there still may be other leaks, like if the return's mispredicted to a call site that leaks the dead register RCX, which happens to hold a secret due to register allocation. To reason about these remaining leaks rigorously, we need a formally grounded way to identify Spectre leakage in static constant time programs. And so that takes us to our final challenge, which is that how existing approaches fail to capture the root cause of Spectre leakage in constant time and static constant time code. So prior work primarily focuses on transient access instructions. Access instructions simply load secrets into registers. But in our example, the access instruction is sequential, not transient. So that means that these approaches don't tell us how to prevent this sequentially accessed secret from leaking. Instead, we propose this new concept of taint primitives. These are instructions that cause a publicly typed register to transiently hold a secret. This return instruction is a taint primitive because at its transient target, register RCX is publicly typed but holds a secret value. And so we prove in the paper that taint primitives are a necessary ingredient to all Spectre leakage in static constant time programs. It turns out we can actually say quite a bit more about taint primitives in static constant time programs. In fact, we prove that in such programs, all taint primitives fall into one of the 4 classes shown on this slide. So first, we have non-constant address loads, or NCAL, which are loads whose addresses are dynamically computed from data at runtime and therefore may access out-of-bounds secrets. Second, we have non-constant address stores, or NCAS, whose addresses are similarly computed from data at runtime, but in this case can store secret data to an out-of-bounds public memory location. Third, we have uninitialized stack loads, or stack-L, which may bypass an initialization store to read secret data from a stale stack frame. And finally, we have secret in non-argument register, or NARG. This is a call or return that can be mispredicted to the wrong target expecting a public argument in a caller secret register. So finally, we present Serberus. Serberus uses the theory of taint primitives, supported by hardware speculation constraints, to harden static constant time code against Spectre attacks, exploiting any combination of these 5 widespread speculation primitives. It does this using 3 compiler passes, which collectively eliminate all taint primitives from all transient executions of the program. And we've implemented each of these passes for LLVM. So the first pass is function private stacks. This assigns distinct stacks to each function in order to eliminate taint primitives due to stack sharing, aka stack L. The register cleaning pass zeroes out registers at calls and returns to eliminate interprocedural taint primitives, that is, the NARC taint primitives. And the final pass to run, fence insertion pass, inserts a minimal number of speculation fences to eliminate the 2 remaining classes of taint primitives the former 2 passes don't handle, that is, NCAL and NCAS taint primitives. And so it's important to note that Serberus is 100% programmer transparent. Serberus does not require any kind of secrecy labels or any kind of annotations from the programmer. All that it requires is that the input program satisfy static constant time, and secondly, that the programmer enable Serberus by passing a single compile time flag. So first I'll give a brief example of how the function private stacks pass works. So this pass comes from our observation that the stack L taint primitive is due to the fact that procedures allocate their stack frames on the same shared stack, allowing a publicly typed stack load to read a stale secret from another procedure's old stack frame. So let's see how this works with an example. So first, suppose we call this secret processing function foo. So it reads a secret and stores it to stack variable x after allocating its stack frame like this. So it stores its value to x and then returns without zeroing out its stack frame. Then we call a non-secret processing function, bar, that only accesses public data. It happens to allocate a stack variable y at the same slot as x. So we call it allocates its stack frame. It tries to initialize y with 0, but as you'll see in a second, the subsequent load of y executes before the store to y executes, allowing the load of y to read the stale secret data on the stack like this. And as a result, we have a stack L taint primitive that results in leakage. So our solution is to simply allocate a private stack to each procedure on which it exclusively allocates its stack frames. This eliminates all stack L taint primitives from the program. The register cleaning pass is what eliminates the taint primitive we identified earlier in load 32. This pass zeroes out the secret in register RCX before return, thereby eliminating the NR taint primitive and therefore any leaks associated with it. So the final pass to run is the Serberus's fence insertion pass. This frames optimal speculation fence insertion as a min-cut problem over the transient control flow graph of each procedure. First, it constructs a transient control flow graph representing all possible transient execution paths through the procedure. Then we identify a set of source sync pairs whose sources are NCAL or NCAS taint primitives, and sinks are either dependent transmitters or interprocedural control flow instructions like calls or returns. Then we run a heuristic min-cut algorithm to identify a set of transient control flow edges, which we remove by inserting speculation fences. So we evaluated Serberus against an insecure baseline and 2 composite state-of-the-art defenses. We show the security guarantees of those defenses in the table on the right. And we benchmarked all of these on a variety of crypto primitives from OpenSSL, libsodium, and HACL star. A subset of those results are shown here on the slide. On average, Serberus only exhibits 21% overhead across all benchmarks, and only 7% overhead across those benchmarks processing larger inputs. That is half of the next best mitigation, despite Serberus offering stronger security guarantees. Okay, so here is a qualitative comparison of Serberus to prior work, specifically prior work that targets constant time code and is deployable on existing hardware. So first off, all but one mitigation targets only a single speculation primitive. In fact, most of these mitigations only target conditional branch prediction, or aka PHT. Also, all proposed mitigations for speculation primitives other than PHT just disable the speculation rather than secure it. That's signified with this delete symbol. In fact, even if we compose the best mitigations for each individual speculation primitive, listed here as securest state-of-the-art, the result will still not mitigate Spectre RSB, and it disables most kinds of speculation. So in contrast, Serberus is the first mitigation for constant time code to, first off, mitigate return prediction, RSB, and it's the first mitigation to permit secure indirect branch prediction and secure stored load forwarding prediction. So I've skipped over a lot of things in the paper. So first, we introduce an operational semantics called ASP, which stands for Abstract Speculative Processor. So this models transient execution on a speculative out-of-order processor. We use it to formally define static constant time programming, taint primitives, and Serberus's 3 passes. And finally, we prove the correctness and security guarantees of Serberus as a set of passes over ASP programs. So just to conclude, Serberus is the first defense that's deployable on existing hardware today that comprehensively protects constant time code against Spectre. Serberus offers both stronger defenses and better performance than the state-of-the-art. In our paper, we provide a complete proof of Serberus's security guarantees. If you're interested, please check it out. And we're working towards upstreaming Serberus into LLVM. So if you'd like to learn more, please read our paper. And if you're interested in learning Serberus and using Serberus to secure your code, please contact us. Thank you.